Welcome to the course Structure Analysis. Myself, Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the 7th lecture, and today we are going to discuss about the slope deflection method. Okay. So far we have seen what is a property cantilever beam, how to solve the property cantilever beam, and how to draw the shear force and bending moment diagram for a property cantilever beam. Later we have discussed about the degree of static and kinematic inervancy, and today's our topic is introduction to slope deflection method. Okay. So what is the purpose of this lecture? At the end of the course, the student can able to derive the slope deflection equation, and also they can able to apply the slope deflection concept to solve the continuous beams. So what is mean by a slope deflection method? So it is first of all, it is a displacement based structural analysis techniques, particularly used for to analyze the statically indeterminate beams and portal frames, particularly for a continuous beams. So this method establishes a relationship between the number of end moments and then corresponding relation and displacements. Okay, so it's generally a displacement method. So in a stiffness matrix method also, we use the slope deflection method to calculate the end moments. What are the applications and then consideration of this slope deflection method? So this method is useful for analyzing the structures, real life structures like bridge decks and building frames where continuous beams are used commonly, with high degree of structural rigidity is required. Where and all the high degree of structural rigidity is required, we are going to use this method. And this method assumes the rigid joints. Okay, whatever may be the joints. For example, generally we know in bridges and all, we are going to have the simply supported condition. But in this method, we are going to assume it is a rigid joints. So what is the meaning? Meaning, the angle between the connected members do not change. For example, now the angle is 90 degree. After the application of load, after the deformation also, we are going to consider this theta angle between the column and beam is not changed. Okay. And then this method have the advantage to account for support settlement also. So we know that support settlement is a common problem in the bridge engineering. So in the bridge, we are going to have the series of piers and then abutments. If any one of the support sinks, then it is going to cause the additional moments to the adjacent columns and then beam column connection, how it is accounted in the problem. So slope deflection method have the provision to account the support settlement also. So that also we are going to discuss. And then this method is more practical for large complex structures, and also this method is easy to do the computer programming also. That's why this method is famous. Okay. Then now we are going to see the derivation of a slope deflection equation. So we are going to derive the slope deflection equation for a continuous beams and portal frames, and then in next lecture, by using the slope deflection derivation equation, we are going to solve the numerical problems. Okay. So as I told, this method is applicable for statically indeterminate structure. So today we are going to discuss about the continuous beams. So let's take a beam. So I am taking a continuous beam. So what is a continuous beam? The continuous beam is a beam which is having more than 2 spans. So if it is a more than 1 span, it is a continuous beam, or more than 2 supports. Okay, here you see this is the span 1, span 2, span 3. Now, for deriving the slope deflection equation, I am going to take this intermediate span. I am going to take this intermediate span. Let's say this support is A and this support is B. I am going to consider only the span AB. Okay, I am going to only consider the span AB. Let's put this remaining adjacent span in a dotted line. So here I am going to have the another span. Here also I am going to have the another span. So what I have done? Simply I have taken the span AB alone. Now this point support A, the support A will be subjected to the rotation. For example, this is the beam. When it is loaded, the support A and B is subjected to the rotation because it is a simply supported condition. Okay. So, how this beam first of all it will deflect? Let's mark it in the different color for a better understanding. This beam is going to deflect like this because it is a simply supported beam. So, what I am going to do, I am going to consider the support settlement also. So, slightly modify the deflection pattern of this beam. So, this beam is going to deflect like this. Okay. So, our B support is somewhat shifted to in the below position because we are going to consider the support settlement delta. Now, what are the theta? So, here one angle will be formed which is theta A, and then here the another angle will be formed. Okay. So, that is theta, this is theta B. Okay. So, one might ask why in A rotation is different, why the support B rotation is different. It is nothing different. The thing is at support B I am considering the support settlement, that is why the deflection profile is like this. So, what are the things we are having here? We are having the rotation at A, rotation at B, also we are having the deflection, support settlement, displacement which is del. Okay. So, we know since it is an intermediate support, even though it is a simply supported condition, if it is an intermediate support, it is going to transfer the moment. So, here there will be a moment MAB and here there will be the moment MBA. So, that moments we can able to calculate by using the slope deflection method. We will go step by step procedure for a easy understanding. I am going to write down the first step to derive the slope deflection equation. The step 1 is I am going to convert the span AB as fixed. I am going to convert the span AB as a fixed. So, the span AB earlier it is a simply supported. Now, you can able to see that I am converted that into the fixed beam. Okay. If it is a fixed beam, here I am going to have the moment, say this is support A and support B, and here also I am going to have the moment. Because of this fixity, whatever the moment is created, that is called as a fixed end moment. So, in order to differentiate that, I am putting MFAB is a fixed end moment at A and MFBA is a fixed end moment at support B. So, we just marked the fixed end moment. Here you should understand the difference between the final moment and then the fixed end moment. Fixed end moment means in the superscript I am going to have the letter F, MFAB. So, this is the fixed end moment. Simply if it is a MAB, then it is the final moment. So, this is the final moment. So, please understand the difference. Then I am going to write my step 2. I write my step 2, release. So, release the moment at any one of the support, at any one of the support. What does means? We have a fixed support at A, we have a fixed support at B. I am going to release any one of the fixed support. So, let us consider I am releasing the support fixity at A. So, at support B, I am going to have the fixed support as it is, but in support A, I released the fixity. Okay. Now, how this beam will deflect? This beam is going to deflect like this. So, it will form the angle theta A. There won't be any theta B because the fixed support, at the fixed support the slope is 0. Okay. At the fixed support slope is 0. Now, let us mark the direction of the moment. Okay, let's mark the directions of the moment. Now, what is the moment here? Because of this deflected theta, there will be the generated moment. That moment is nothing but 4ei by L into theta A. Okay. Here there is a deflected shape and there is a theta which is a theta A. How this theta A is generated? Because of that moment. What would be the moment? That is nothing but 4ei by L theta A. Now, what about the moment at support B? 50% of the moment at support A will be transferred into the support B. What is the 50%? Then that is 2ei by L into theta A. Okay. So, at this point there will be the rotation because of the loading condition. How that rotation takes place? Because of the moment. What would be that moment? That is nothing but 4ei L by theta A. Okay. Let's go to the step 3. In step 3, what I am going to do? This time I am going to release the moment at support B. Release the moment at support B. So, this time I am going to have the fixity at A and release this moment at the B. Okay, let's mark the moment direction. So, clockwise, clockwise. Now, let's draw the deformed shape of this beam. This beam is going to deflect in this way. Because of this, I am going to draw the tangent and then this is the theta B. Then what would be the generated moment here, which is nothing but 4ei L by theta B. Now 50% of the moment will be transferred to the adjacent support, which is 2ei L by theta B. Okay. So this is step 3. Then step 4. Let's consider step 4. Now I am going to consider the support settlement. I am going to consider the support settlement. So, I am going to consider any one of the support is going to have the settlement. So, if it is settled, it will be like this. Let's have the support A and B. What I am considering here is support B is settled for the quantity of del. Support B is settled. The support settlement is I am considering the del. So, because of this, the generated moment here is nothing but 6 ei by L square multiplied by the del. Okay. Then what would be the moment here? You may tell the 50% of the moment is transferred. No. For in case of support settlement, the 100% of the moment also will be transferred to the adjacent support. So, here also we are going to have the 6 ei L square multiplied by del. So, 100% of the moment is transferred. So, I am going to calculate the final end moment. Calculate the final end moment. I am going to calculate the final end moment. So, what are the things I want? Let's draw the beam here. Let's draw the beam here. This is A and this is B, but before that I have one support here. Okay. So, it is a 3-span continuous beam. Okay. I am going to write the equation for MAB. What I am going to do? I am going to simply add the values in each and every step. So, what is the step 1? In step 1, I am having the value of MFAB, which is a fixed end moment. So, here equal to MFAB. plus. In second step, what is the value I am having? In second step, I have 4EIL by theta A, which is acting in a clockwise direction, so positive. So, I will be having 4EI by L into theta A. Then I am going to add the value in the third step. So, in third step, what is the value? The third step, 2EIL by theta B. Let us add that value, 2EIL by theta B, 2EI by L into theta B. Now, what is the value in the fourth step? Fourth step will be having 6EI del by L square, which is acting in an anti-clockwise direction. So, we need to consider the negative sign, which is 6EI by L square multiplied by del. Let us simplify this equation. MAB equal to MFAB. Here one might ask, sir, MFAB also in anti-clockwise direction, but you are consider the positive sign here. It's nothing like that. When we are solving the problem, automatically I am going to put MFAB is a negative sign and MFBA is a positive sign. So, while solving the numerical problem, we are going to understand that concept. So, plus 2EI by L I am commonly taking outside. Okay. So, what is the leftover here? 2 times of theta A plus theta B minus 3 del by L. Because already I have taken 2EI by L outside. So, another L will be left over in the denominator. So, similarly, I can able to write the formula for MBA. So, MBA is equal to MFBA. This time I am going to add in all the steps the right hand side direction, right hand side values, this value, this value, this value and this value I am going to add. So, if I add, so what I am going to get? 2EI by L into theta A plus 4EI by L into theta B minus 6EI by L square into del. Let us simplify this. MBA equal to MFBA plus I am taking 2EI by L commonly outside. Then let us write this term first, which is I am going to get 2 times of theta B plus then you are going to write this term. So, theta A minus of 3 del by L. So, we just formulated the equation. Let us consider this is equation 1 and then this is equation 2. So, we derived the equation for final moments by using the Stokes deflection method. So, if it is a multiple supports given also, easily we can able to write the formula, that also I will explain. Okay. Simply I am going to take a continuous beam. Okay. So, let us say this is A, support B, support C, support D. So, I am going to quickly write the final moment formulas. MAB is equal to MFAB plus 2 times of EI by L into 2 theta A plus theta B minus 3 del by L. So, equation 1. Let us write the formula for MBA. MFBA plus 2 times of EI by L into 2 times of theta B plus theta A minus 3 del by L. This is equation 2. Let us write for MCB. So, MFCB plus 2 times of EI by L. So, this has to, for example, MFCB is there. C comes first, B comes next. So in the first term, we need to put 2 times. That's the way we can able to remember easily. So 2 times of theta C plus theta B minus 3 del by L. So equation 3. Then M, we put a value BC. Now we have to go for the value CB. Sorry. Let's erase this. Yeah. AB is over and then BA. So then this supposed to BC, I supposed to write here BC. So I supposed to write the BC here. So this is BC. And this is, let's erase this equation and write once again. Yeah, now write. So this is for BC. So MFBC 2 times of theta B and theta C. Okay. So BC is over now and then I need to write CB. MFCB equal plus 2 times of EI by L into 2 theta C plus theta B minus 3 del by L. So in this way we can able to write the equation for n number of span also. All you need to remember is it starts with AB. So 2 times of theta A and theta B. It starts with B. So 2 times of theta B and theta A. It starts with B. So 2 times of theta B and C. Okay. And it starts with C. So 2 times of theta C and B. So this is all you need to remember. So in this lecture, what we have seen, we have learned how to derive the slope deflection equation, and also we understood how to apply this concept in the problem. Okay. So in the next lecture, we are going to discuss the same equations with the numerical problem, and then we are going to calculate the final end moments. Okay. So thank you for watching this lecture. Thank you.